Thank you very much, and good morning, everyone. Thanks for the warm introduction and having me speak here. So, I mean, given that I realized I have half an hour, I removed the visual part, so I focus on compositional reasoning over natural language, leveraging neuro-symbolic AI. So let me start with an example. This is an example called visual question answering, problem setting that is well known to vision and language community. The problem setting is as follows. So you have a question like, is the red bike to the right or to the left of the Asian people? And then look at this image in 2D, please. And the answer is right. And we tested a model that was a really nice neural model specialized for this task. And the answer is right, so it is correct. The question is complex because the model needs to recognize not only objects like bike, people, but also composition of the attributes and objects like red bike, Asian people, and also the relationship like the left, right. So the whole configuration of the scene should be understood by the model. However, then we had another test. This question was not in the data set, like, is the red bike to the left of the Asian people? So the question is similar meaning kind of, but it seems to be simpler because it's yes, no. So the model says here wrongly yes, while the answer should be no, according to the previous one. So this might make us to worry about does the model understand objects, attributes, and relationships? You might argue this is old times. 2019 is ages ago. So now we have large vision and language models pre-trained on huge amounts of data. We can even augment examples. We can do paraphrasing and add questions. These are the practices that have been done often recently. And then you just augment, and then your model becomes so-called robust to question variations. Let me show you another example. Here is newer from 2023. So this is Dali, a woman with an apple in her left hand standing to the right of a car. And Dali can visualize, it's a diffusion model, 12 billion parameters trained with huge amounts of data. And you see almost all of these top figures have the woman having the apple in the right hand. The car and the position of the car and woman is kind of random, it seems. The objects are recognized very well. There is an apple, there is a car, there is a woman. But again, this is April 2023. You might say this is still old. And if you try it, Gary also mentioned, you might get better results now. But what is the key point here? These models, of course, are improving as the observation increase and the models enlarge. However, we want the generalizability on observed cases. We want to make sure these models capture basic skills of reasoning, and also lack of interpretability, why the apple is always in the right hand. Maybe people are mostly right-handed, that's why this image is generated. Maybe the left of the image with the left of the person is confusing for the model. We don't know why things go wrong or right. And then, of course, there is always a need for huge amounts of data. So these issues are problematic in applications of natural language and computer vision, though there is a hype that we think, okay, these models are doing impressive in these kind of applications. So in my group, heterogeneous learning and reasoning, we try to deal with these problems with different aspects. We do evaluation and benchmarking of complex reasoning of the large language models. We try to do integration of explicit reasoning with the neuro-symbolic approaches in neural architectures. Also developing software tools that facilitate this kind of integration. And also we have some efforts on grounding language in visual modality and application problems. Like question answering has been an interesting kind of problem setting that has been used in different senses, like spatial question answering, common sense question answering, visual. So people try to have problem settings with different flavors and focusing on different semantics. So we have been trying to use this problem settings to really be able to deal with some of these issues. Today, I will be talking about three aspects of our research. So given the time, first I talk about the spatial reasoning and integration of explicit knowledge in spatial reasoning with LLMs. So we started with creating benchmarks. We realized a spatial reasoning kind of complex problem. This is also historical for me. I have worked on this like for many years during my PhD to conceptualize the spatial semantics in the language. So we try to create a specific specialized question answering benchmark that is focusing on a spatial reasoning. And then it's also the benchmark, it has all concepts and notations with the spatial concepts, like qualitative spatial representations, like topological, directional, and the logical reasoning over the spatial representation. So here is an example of our benchmark. Like this is synthetic data, like 3 boxes called 1, 2, 3, and there exists an image. Box 1 contains a big yellow melon. So there are different of this data set. Some of them says there is a blue circle, blue triangle, but we have variations that says this is melon and apple and so on. But we have complex explanations and we generate questions. So like this, like is the small yellow apple to the west of the small yellow watermelon and so on. We also created realistic benchmarks. Like this is also the data set. We curated this because it was existing. Again, I created this data set with the spatial concepts for information extraction purposes many years ago. But then we created a question answering version of this to be able to evaluate question answering capabilities of the current models. I'll show you some of the results that we had that was kind of less expected. This is kind of 2021, so we used encoder-based language models like BERT and that kind of family. But actually, it was surprising that BERT at that time was like performing above 95% for question answering on Wikipedia kind of like data sets. But this data set was only 30 words vocabulary with just complex nesting expressions. And we saw actually the results are very kind of disappointing. You see for some types of like we have human generated explanation of the same type. And we see like 62%, 70%, and some cases that we had like quantifiers, like is there a box above all the circles? So we have some quantifiers, and you see like the yes/no questions are very poor, like 39%. So this was really kind of interesting that we saw, okay, there are lack of reasoning with the language models when we have complex nesting structures, even with simpler and limited vocabulary. But there were some advantages to this practice. So we had a benchmark already, and we saw, okay, synthesized data can help when you use them for fine-tuning. They can help transfer learning for different domains. That was a good advantage. And then we also had variations that we called it a Spartan with the more coverage of spatial expressions. And we saw that when we have, again, this is synthesized, but it can like apply to other data set. Like, for example, here I will show more results on this data set, step game. We show that we can generalize over more complex settings. And then also we show that training with the synthesized data, again, can improve on the realistic domains a bit. So this was like to just in one sentence, if I want to say the conclusion, the synthesized data was helping for evaluation as well as transferring spatial knowledge to other domains. But this was in the paradigm of all pre-training fine-tuning. However, we wanted to do more interesting things by integration of the spatial logic into like the kind of the large language models, and that was the next practice that we tried. Here I give an example what I mean by integration of spatial knowledge logic. We have the context like a white rectangle is on the orange rectangle. Here is the picture. There is also a red rectangle which is above the white rectangle. And then the question is that, is the orange object below the red one? So the model needs to do a bit of transitivity to understand this. And we have like small formal logic. We developed this in Prolog, and we can just infer different facts from it. Like we have some rules like right is opposite of the left, or we can, if we can say A to the right of the B, then B will be to the left of A. If X is above B here, and B is above C, then X is above C. So just transitivity rule and some rules of that type. So this was our spatial logic. And then we have initial facts, like formally, if we represent them as triplets, like red rectangle, white rectangle above, and then white rectangle, orange rectangle above, and we want to answer this query. So the advantage of the data sets that we created was that we had the chain of logical reasoning as well. So for the training data, we can see, okay, if there is a white above the orange, and then we can use this converse rule and say orange below white, and then red above white, we can say white below red, and then with transitivity here, we can say orange below red. So we can have this all in our data set, and then the good thing is that we could use this instance-specific like logic that and use these chains of reasoning and transfer them or convert them to a kind of constraints that if the question one is or the fact one is correct, then by these rules I have to have fact two also being correct. And if I have fact two correct, fact four should be correct, and if fact four and three are correct, then the target query should be correct. So basically, we generate some equality constraints between the inferred intermediate fact and the final solution. And then this is the advantage of this is that we just do this in the training time. Of course, in the realistic setting, we cannot have such a mapping easily. So this is only for the purpose of training. And then we can have training paradigms. This is kind of approach that many people use, different variations of this. Like you have like a task loss that says you have to be correct with the task performance, the answer of the question, usually cross entropy loss. But also we have the constraint loss, that we have the constraints logic, the equality constraints, and then we try to minimize the violation from these constraints. So this could be just formalized as like kind of a dual formulation of the objective subject to the constraints and have Lagrangian multipliers here. This is an approach that also Mouse is here, like they had this approach in Neuro-IP's paper. We use this approach, implemented that, and we use this approach here to really integrate our spatial logic into the models. So this can be integrated both on like encoder-based or BERT-like language models, as well as generative ones, as far as we just adapt the output to classification setting. Let me share some of the results here. So this data set is rescue is our realistic one, the gray car in front of the house, that kind of data set. And then this was interesting that when we integrated the logic, this is BERT plus Q chain, we saw that overall very little improvement, but then we looked at the data set and we tried to divide the questions to the ones that needed more steps of reasoning. This was natural data, so it was less steps of reasoning involved. And then the null class was the class that was hard for us to see, okay, if this is really how many steps are needed, and sometimes it was common sense. So we divided that and we realized when we have really explicit steps of reasoning, then the Q chain is improving better. We had also a T5, which is generative model experiment, and we added this Q chain on fine-tuning with T5, and we saw better improvements. However, I included GPT results. GPT is not perfect, it's like around like 66%, and GPT-4 is 77%. It's still not very impressive, but better than what we did with BERT. You see like type of errors that can be done with GPT here. However, one interesting finding was that when we used this data set that you heard from me, the name like a step game, this data set has like splits of 10 steps of reasoning. And then we see that this result, the last two rows of the results taken from another paper, we didn't repeat because of the cost. So they reported this 31 and 25% accuracy only with GPT. So this is really poor. And then we realized that if we have this fine tuning with BERT, we can even do much better than GPT when we do training with the symbolic logic. So this was interesting. So our finding, to just summarize from this part, like we saw that pre-trained language models are comparatively weak in spatial reasoning. So we created these benchmarks and synthetic data to evaluate them. Synthetic data could help a bit of by fine-tuning with synthetic could help a bit of transfer learning, but then logic-based fine-tuning was helpful for multi-hop reasoning. But we realized that GPT actually, when they fail in the deep reasoning, like when you need to do connections and do global reasoning, but they did better on common sense questions, at least in our case of experiments. So it seems these models are really capturing common sense from the information that are exposed to. So let me show you another practice that we did for dealing with uncertainty, or like question answer probabilistic reasoning based on LLMs. So here, what I mean by probabilistic reasoning, there are probably different like understanding of this, but this is what we mean by that. This is an example of a example of logical reasoning. When you have David is big, if someone is big, then they are green, and if someone is green, then they are round. Now we want to conclude David is round. This is taken from a data is called rule taker from AI2. And then we try to augment this with probabilities. And we had variations with probability, actual value, numerical values, as well as adverbs of uncertainty. Like we have David is big. Usually if someone is big, then they are green. So usually it's something like maybe 90%. And then we have normally if someone is green, then they are around, then maybe this is like 80%. We assign values actually to this, and we create the data set. Then now we say David is round only with a probability of 72%. So now the question is like David is round, the model say, okay, should generate the probability value. So why this is important? I think this is interesting for the medical domain. We have a lot of uncertain evidences from different like places. For example, you say people with diabetes often have many of the same risk factors associated with heart disease, and there might be even in like medical domain, you can even probabilities as values mentioned in the text. So we want to bring evidences together and infer what is the probability of this person having a heart attack or something. So here is like more extensive example of what we did. This is not actually, we were inspired by a different benchmark that is called Rulberg, but the issue with that was that the knowledge or the rules of reasoning that were probabilistic were applied to the whole data set. For example, if I say, if people are cousins, they will not marry, or they will marry with 20%, then maybe it depends really on the context. And so we wanted to have different rules per example. So we really wanted the model to look at the rules that is given to it and reason based on that, not capturing the rules from training from the data. So that's why you can have contradictory rules. Like the first question might say round people are green. Another question say round people are not green. So we really want the model to look at the context and the rules and then do reasoning. So the way that this works here again is like assign probabilities to the facts and rules, and then compute the answer based on the rules of reasoning. So the thing that we could do here was to again same kind of approach, try to make these rules of probabilistic reasoning or the actual computations for computing joint probabilities to some equality constraints. Again, we have intermediate rules and facts, and then we can generate this equality constraint that says probability of fact 1 multiplied by 90 should be equal to probability of fact 3. So then when we have these equality rules, we can again do the same approach. We can have this as a constraint and try to minimize not only the answer accuracy, but also violation from the constraints. So our results show that these pre-trained language models, in particular for deeper networks of reasoning, probabilistic reasoning, they could be improved with this approach. And then they also can transfer learning. So it's kind of consistent result. We can transfer learning to other domains. Here, just sharing some of the results, what this paper actually published, so you can see all the detail and experiment with the loss variations. So this is Roberta model, that is an encoder-based language model, and Roberta plus probabilistic constraint training. The bolder blue shows better results. So you see the lower table is bolder. These are depths of reasoning, and these are depths of models, and this is constraint satisfaction. So we see that we could improve a lot with the depths of reasoning for all these aspects. So some other experiments in the same line I wanted to share was, okay, nowadays we might not want to fine-tune the models because they are expensive, they are sometimes black box, not available. So people do a lot of practices to like impose constraints or symbolic reasoning or like code aided, like PAL, programming aided language modeling to be able to deal with the problems at the inference time only. So here we try to do some practices with the like inference time, just prediction time, symbolic reasoning for dealing with the probabilistic questions. Again, a context is given, like green event is true with probability of 80% and so on. And there is a query. And then here we did the usual practice. Let's do just prompting, like give the question, solve this, give some instructions, solve the following probabilistic question and generate the probability of the answer, only provide number between 0 and 100, and then give the context and the query and the answer as an example. Or do chain of thought, give me the process of reasoning and give example of the computation also, and then ask the model to answer. So these kind of types of few shot or chain of thought, actually with GPT 3.5 and GPT 4 was kind of really near random. So the models couldn't really infer the probabilities. But we had practices for mapping to code and also like even Python code or even MCMC algorithms related to the problem by extracting the probabilistic graphical model, like Bayesian network behind this text. And then we also had the best practice was to map the problem to problog code, so probabilistic logical code. If people are familiar with that, this is probabilities in problog, and then the logic, and then augmented with probability values. And you can ask queries like, what is the probability of green and pink here? So this was interesting that we could see that mapping to problog was really improving the results. And with GPT-4, we could get really near perfect kind of like syntax. And then we could just give it to the external solver to solve it for us. So this was also something, and you can see more details. This paper is archived under review, so you can see more results about different variations of this kind of mapping method. So with that, I wanted also, how much time I have? Like probably 5 minutes. You can take 5 minutes, okay. So the last part, a few minutes, I wanted also to talk about a framework, because this kind of approaches we found useful in different contexts. I just gave you 2 examples of probabilistic reasoning and spatial reasoning. But I mean, nowadays we see that the frameworks and the software, we can program with PyTorch, deep learning is advancing, the tools are so available and nice. But when you want to integrate symbolic knowledge, it's very hard to program for this. So that's why we worked on development of the frameworks that help this integration. The motivation is that the intelligent systems need really to look at concepts, properties, and relations, composition of the concepts, nesting structures, and we want to look at the interaction of the models really, and we need to do decisions based on the models, not single classifiers or regressors. So that's why we need a different level of modeling nowadays, it seems, and the current tools don't support that. So here, I think I will skip this. I just wanted to show why the knowledge is helpful, what I mean by models. This is briefly saying this is an entity relation extraction when you have separate classifiers that says Washington is a location here, this one, and this one says, like here, Associated Press is an organization, and then here says the relationship you work for. But if I have a piece of knowledge that says people can only kill people, but people cannot, like locations cannot work for organization, then we see that we are not consistent with this knowledge, and we have to, like maybe the model can really say, okay, I gave up location, I say Washington is 90% because I have to adhere to this constraint. So this is the way that we have multiple models give us probabilities or scores, and then we want to be consistent with these rules. So how we want to program this, we need paradigms that actually need data modeling, knowledge representation. Of course, the learning should be there, and designing different inference and learning paradigms. So we have a framework called dominoes that we try to do this. To underline is PyTorch, but we have a symbolic interface, symbolic representation as an interface. And then the knowledge can be expressed with logical expressions and quantifiers. And then we can connect these names or symbols to the neural models, whatever model that you want. It could be language model or like any design feed-forward architecture or anything that can give you a probability distribution. And then we can reason over the symbol and integrate like symbolic reasoning, because we have the power of representation here. The symbolic reasoning could be on the output variables or latent variables, and then we can integrate this into deep learning. So the logic actually now current status is that we map it to constraints. So the experiment that I showed you partly are done in this framework actually, and then we have a variety of algorithms underlying. So for the interest of time, we have like the components of this new programming paradigm is declarative problem specification, defining computational units that could be wrapped as learners, and then we can have the logic expressed. And this logic can be used now. We have the integer linear programming as underlying, and also we have different training paradigms. This is an example of the way that we write the code, like words are concepts, phrases are concepts, sentences contain words, or sentences contain phrases. A person is a word, a person could be a phrase. So you can really write the concepts and then connect this, like you can write the logic between the concept that these labels are disjoint. And then you can also like connect learner modules to the concept. Here we have a demo and also some like a website if you want to look at the details of this tool. We have multiple algorithms implemented, like inference mask loss is our paper, and also we implemented papers from Mausam group and also Hivanden group. So we have different algorithms implemented underlying, can be used easily. And then you don't need to worry about the integration optimization. You just need to write your logic and do your deep model design. We have a benchmark called glucons that we tried many data sets and tried to test and provide a benchmark for people to really test how integration of constraints can help. So this is covering multiple tasks like from classification, question answering, even Sudoku-like that you have only the constraints and you want to see if the model captures like solution based on just iteratively going over minimizing the violation from constraints. One last practice that we did recently is like, now we have this declarative representation, and we think that, okay, natural language to code, I mean, here, we don't have really like any like impressive results about natural language to deep modeling. But here, if we have a declarative interface, then this is closer to natural language. Then we can have natural language to declarative modeling and go from there. Natural language can go to the formal constraints. And I think this is exciting about the large language models, that they can give us this kind of formal representations easily because they are capturing format easily. And the surface structure in the surface, so we can get the code, and then this code is really involving all the underlying computations that we want. Just to summarize, I showed our results on evaluation and reasoning skills of language models, how we integrate explicit reasoning in a couple of applications like spatial and uncertainty reasoning, building tools, and then maybe like the ambitious goal is like maybe we can have like natural language interface to declarative programming. We have done this partly, but this is on in progress. I should thank my group. This is outdated, the slide, sorry for that. But my PhD students, my postdocs, and our collaborators at IHMC for helping all this like research to be done. Thank you very much.
So we have time for one question.
First question is, can we think about moving this microphone to the side so it's possible to capture the slides for most of the audience? But the other question is, a lot of those tests that you put up in the early part of the talk involved things like left and right and up, where it's very difficult really to resolve what the frame of reference that should be used is. It might be difficult even for human beings. So I wonder whether we are presupposing, in the same way that, say, microtheories were designed to make explicit the context in which reasoning should be done. I wonder whether in a lot of these tests that we're giving to these systems, we're presupposing a context that they in fact don't have, because they are not us trying to do these tests. And this is a problem for testing of AI systems generally, that we presuppose humanity in the thing which is doing the test, and then get mad at it for not satisfying that opposition. This is not a general defense, but I think it is a defense against quite a lot of the examples which are used to beat these systems with. So what do you think about that, and how might we improve?
Yeah, I think this is a great question. I mean, we have all this conceptualization from the cognitive studies and how frame of reference plays a role in explaining the spatial relations and all. But I think that is really the way to go for. I mean, that is why I'm fascinated by symbolic reasoning, because those studies can be directly integrated into our modeling. So this question answering maybe was naive and to like 2D like images, but we do work that I didn't have time to look at, like navigation and instruction following, that is even more serious, that when you explain to the robot, go to the thing that is to the left, or is it like egocentric, is it robot centric, is it really object intrinsic like positions. So I think these are really things that we need to have like in hand with like learning from observations, how to use this frame of reference, as well as like modeling and then like use these tools in the neuro-symbolic era. I think that is a great like kind of opportunity we have to integrate this. But yeah, this is a very challenging problem.
I love your research program, by the way. I think it's got a chance of really driving significant progress. So
Thank you so much.
I've already sent a bunch of your papers to my students.
Thank you so